Hello, and welcome to the Lab Water Source, an interactive webinar series where we wade through everything from the fundamentals of buying and maintaining a laboratory water purification system to ensuring the water meets your application needs. I'm your host, Jeff Scheibel, and today's presentation is Pure Water 101. Today's presenter is Julie Foster. Julie is a PhD and the Global Product Manager for the Water Purification product line at Thermo Fisher Scientific. In this capacity, Dr. Foster manages the product line lifecycle from strategic planning to tactical activities. This webinar is being recorded for future playback. As registered guests, you will receive a link to the recording in your email when it becomes available. Our presentation, including Q&A, will last about an hour. Please type any questions that you would like to ask into the text box in the Q&A module that you see in the right side of your screen. Julie will be taking relevant questions throughout the presentation. You'll be asked to participate in this interactive webinar by answering various survey questions that we posted throughout the presentation. The results will then be shared so that you can compare your answers with your peers. This ends the preliminary instruction, so without further delay, I present to you Dr. Julie Foster.
Thanks, Jeff. I want to personally welcome all of you to our first webinar in this series called the Lab Water Source. We developed this webinar series to respond to frequently asked questions regarding lab water. During the webinar series, we will introduce you to different topics in lab water purification, starting here at the basics with Pure Water 101. So the goal of this webinar series is to empower you to make good choices regarding lab water. During the series, we'll discuss how to purchase the right system for your application, help you understand how your system works, and perhaps most importantly, empower you to understand how to keep your system running correctly. This information is not specific to a thermoscientific water system. It can actually be applicable to any water system you are already using. So let's start with Pure Water 101. And just to get you oriented to today's topic, here are the highlights. Why does a lab need special water? What are some of the tap water impurities? And what are the technologies that a water system uses to remove these impurities? What are the types of lab water that you might need in your lab? And then we'll peek inside of a water system to see how it employs all these technologies to purify water. At the end of the webinar, we'll have a Q&A, and this is really dedicated time to ask questions. But if you do have a question that comes up during the webinar, feel free to type it in, and I'll do my best to address them as we go along. And if I do miss them, we'll revisit them during the Q&A. So let's kick off the webinar with an interactive survey question.
Thanks, Julie. Our first question, what is your primary application? Using the survey question module, please select your answer now. And again, if you have a question for Julie, you can ask it using the Q&A module that you see in the lower right corner of your screen. I'm going to give it another moment as answers are still coming in. Okay, let's broadcast the results and hand the reins back to Julie.
Thanks, Jeff. All right, so we're pretty evenly split, analytical, life science, general, and then we have some none of the above. Not too surprisingly, the analytical and life science are definitely on the more sensitive end of the spectrum in terms of applications that you might be doing. And general lab use, again, something normally every lab will need some water for this kind of, for general lab use, but we'll get into that here in a minute. So let's just kick this off by explaining or thinking about why a lab would need special water. And when I mean special water, I'm asking the question, why don't we just use tap water? If it's safe enough for all of us to drink, why aren't we using it more in the lab? So I have a graphic here on the left of a water droplet, kind of a typical lab or typical tap water droplet that has salt and bacteria and organics and nucleases. And one of the points that I would want to make right up front is that tap water from even your house to down the street, to a different city, to a different country, really different. So the makeup of this tap water can really be varied. But in general, it really tends to have a lot of each of these things. Safe enough to drink, so not so much that it's going to hurt you, but could cause trouble with your experiments. For example, if you follow the first arrow up to the filters, you see a clean white filter and a filter that's clogged with what looks like maybe organics or bacteria. That's kind of the first sign of trouble. A lot of lab equipment that we have in our lab have filters that we need to change periodically. And so if we're using tap water through that filter, they're just going to clog quickly, driving up your consumable cost and requiring you to maintain the system more frequently. And the same example to the right of that is the shower head that has the mineral deposits. That's something probably you're really familiar with even at home. And tap water, again, safe enough to drink. The ion level is okay, but when you're running it through pipes and exposing it to metal and using it throughout the house, for example, you're going to get mineral deposits when there's too much salt in the water. So if you think about using tap water in equipment like an autoclave or a glassware washer, and you think about these mineral deposits, it's not a great thing to have happen to your expensive equipment. So as much as you can avoid that, you want to. Then in the middle arrow, it's pointing to an HPLC trace. The top trace, you can see it's in very small print, is deionized water. So deionized water removes ions. It doesn't remove organics, which is what an HPLC trace will look for. So you see all the peaks of impurities that are in that water. So DI water is not a great choice for use in HPLC. Below that, HPLC grade bottled water. Again, bottled water is great when you have kind of small quantities that you need. It comes certified when it's not opened, but as soon as you open it and you're using it, you're introducing atmospheric organics potentially into the bottle. So you may be seeing some impurities from that. The lowest trace and the smoothest trace is water from an ultra-pure water system. And because the water is being produced on demand, it's not sitting around, it does not have any organic impurities that are showing up in the trace. So that would be, if you think about running tap water then through that HPLC, it would probably go crazy and have a lot of peaks, and you would never see your sample within it. Not a good idea for any kind of sensitive analytical methods. And below, the arrow pointing down, cell and tissue cultures are all very sensitive to ions and organics and bacteria and nucleases. They're really sensitive to just about anything that could affect cell morphology and getting you to the point where you have reproducible results. So using tap water in that kind of sensitive biochemical application, not a great idea. So what's in tap water that we have to keep in mind? So ions are probably the first thing you might think of when you think about what would be in an impurity in tap water that potentially affects your experiments. These, the most commonly found dissolved solids that are found in tap water are calcium and magnesium ions, and this is what we traditionally call water hardness. And again, something you're probably familiar with at home. You can taste hard water. It has pretty distinctive taste, so that a lot of homeowners install softeners in their basement or even RO systems, reverse osmosis systems, to pull and remove the hard water. So that calcium and magnesium, even sodium, they all come from rock and soil areas that the water passes through before it gets to your home. And silica, again, another dissolved solid, it has a really weak ionic charge, so it's tough to get out of tap water, and but that's also found in your water. Because of the amounts of ions in your water, it's really important, and it's important to know how much ions are in your water. So you'll notice if you look around your lab and you have a lab water system, the majority of the lab water systems will have a digital readout of the water purity at any time. It's a real-time readout. If you have an ultra-pure water system, it's going to read out hopefully 18.2. So that is the readout of the conductivity or resistivity of the water. So organics, another impurity that is pretty important that we need to keep in mind. Organic contamination really comes from natural sources such as runoff and decomposition. It tends to get worse with rainy seasons, and I think this is important to remember because the level of organics does change in your tap water all the time, and you are feeding your lab systems, a lot of them are fed on tap water. It's important to remember that the seasons will actually affect how well your system's running, and it may affect how often you have to change filters. The more organics that are in the water, the more often you're going to have to change filters. So these impurities really impact any of the experiments that directly measure organics. The one that comes immediately to mind for me is GCMS. Because experiments are becoming more sensitive, customers sometimes want to see a readout of the total organics that are in the product water at any one time. So I just told you in the previous slide that water systems, most of them directly monitor the amount of ions. It's always like reading 18.2 on an ultra-pure water system. That option, there's actually an option out there from most water companies that you can get a digital real-time readout of the total organics that are in your water as well. So it's an option to keep in mind if if your applications are very sensitive to organics and you need to be monitoring them in your water, there's an option, and it's usually called a TOC monitor, Total Organic Carbon Monitor, and that's again, it's available for most systems from most companies. The next contaminant that I want to talk to you about, I kind of grouped these guys together, bacteria and pyrogens. I grouped them together because pyrogens come from bacteria. So bacteria, probably you're really familiar with this if you're doing any kind of biological applications. They are going to have some of the similar risk here as the pyrogens. Pyrogens are also known as endotoxins, and they are the byproducts of bacteria growth and degradation. Even the word pyrogen gives you a clue as to how they can be detrimental to your work. Just think of the little piece pyro. It means heat, and pyrogens basically are agents of heat. If you were to inject somebody with a pyrogen, the pyrogen triggers the immune system, causing a fever. So in biochemical and cell biology experiments, pyrogen contamination can actually alter cell growth and morphology. So there's reasons to be real concerned and careful when you're thinking about pyrogens or bacteria. The same kind of is true of nucleases. Actually, bacteria are one of the main sources of nuclease contamination. So nuclease is the general term for an enzyme that degrades either RNA or DNA. And it's kind of a general name. Specifically, it's called RNase, which degrades RNA, and DNase that degrades DNA. And it can really be a huge problem for any applications in the molecular biology realm, because if it's an enzyme contaminant and it's degrading RNA and DNA, and you need those for your experiment, it's going to be a problem. So if you've ever had a blank PCR reaction gel, I know I've had them many times myself. Probably you have some sort of nuclease contaminant somewhere, and water is suspect. You should think about that. So traditionally, scientists are using either DEPC, it's a chemical to inactivate RNase, or they're autoclaving water. This is actually the method we used in our lab back when I was a graduate student. So DEPC, it's an extra step that you have to do, and it adds cost to your experiment. And autoclaving, same thing. It's got the same drawback. It's an extra step, autoclaving your water. And actually, nucleases are notoriously stable, so they can sometimes survive an autoclave. And then, anytime you have a stock of what you're labeling nuclease-free water, anytime you open it and you use it once, it's pretty much done because you've opened it to the atmosphere. So many people don't realize that you can get nuclease-free water from most type 1 water systems without the hassle of autoclaving or treating the water with DEPC. So this really comes from a type 1 ultra-pure water system that's specially configured, and I'll talk about what configurations will bring you the result of nuclease-free water. Not every type 1 water system will do that. It has to be specially configured for that. So lab water standard, there are many of them out there, and in your lab you may pay attention to one over the other. If you're clinically geared in your applications, you may be looking at a different standard. But in general, this is the most widely used standard, and it really helps to create a universal language when we describe lab water. It's an American standard, but it's actually used internationally. So if you purchase an ASTM type 1 water system from any company in the world, you know that the water that comes out of that system has to meet this standard. So that gives you a little bit of security to know what quality of water that you would get and that you can compare different companies' water. So the ASTM standard names may not be very familiar to you. I don't know if you know your water by type 1, type 2, type 3. I didn't when I was a graduate student. That wouldn't have meant anything to me. I knew them by these names, ultra-pure, pure, and RO water. And even ultra-pure water, I hear a lot people describing that water as 18.2 water. So it all means the same thing. I've also heard it called milli-Q water or nanopure water, all describing type 1 ultra-pure water. So ultra-pure water is the most pure water that you can get out of a water system. The resistivity, which is the measure of ions that are in the water, has to be greater than 18 megaohm. And 18.2 is the absolute maximum. If you had a water system reading 18.3 or anything above that, something's wrong and needs to get maintained. Not possible. 18.2 is the absolute maximum. It is ion-free water. So ultra-pure water, most pure that you can get. Next to that would be type 2 or pure water, and then RO water, which is the least pure out of the mix here. So
that brings us to our second.
Yep.
Sorry there, Julie. That brings us to our second survey question. What types of water are commonly used in your lab? Please select all that apply. Again, I'd like to remind everyone that if you have a question for Julie, you can ask it using the Q&A module that you see in the lower right corner of your screen. Julie will be taking your questions in just a bit. I'm going to give it another moment as answers are still coming in. Okay, I'm going to share the results and turn things back to Julie.
Thanks, Jeff. This isn't too surprising, again, given what I saw with the applications that everyone's doing here. Type 1 water is in most labs unless you really are just doing general chem type of applications. And then the 30% with type 2, type 3. Normally what I see is a lab either has, almost all labs these days have type 1 water. And then they'll also either have type 2 or type 3, and that's what's feeding the general lab equipment. So this is not too surprising. So what kind of water do you need in your lab? This is a table that we extracted from the water book, and you'll have that link at the end of the presentation. It's just a general list of applications and then the type of water that you would need for it. And just a couple of general things to keep in mind. This piece of the table's so big we had to split it up. This piece of the table is the list of applications belonging to ultra-pure type 1 water. And what you'll notice is every single application on this list, they're sensitive applications. They're applications that are sensitive to ions and organics and bacteria and nucleases. So if you're working in any kind of analytical or life science lab, most likely you're going to need a type 1 water system. And then this is the second half of the table where we have listed the applications for type 2 and or RO. which is when I saw your survey questions and they were split between type 2 and RO, totally not surprised because you can use that type of water for a lot of different applications. There's a lot of overlap there. So the pure water, it's not ultra pure, it's just pure, but it's a really great water source to feed lab equipment or to make buffers and media. So just to review what we've talked about so far, like what's an appropriate use for the water, what's not appropriate. Some people, and I've heard this actually quite often, they think, let's just purchase an ultra-pure water system and we'll use it for everything because it produces the most pure water. It should be good for anything that you could throw at it. So here again, I have in the droplet that we have ultra-pure water, and basically in the droplet, there are no impurities because it's essentially impurity-free. So you would think that might be a really great type of water to feed into lab equipment. Unfortunately, what happens is the ultra-pure water, because it is essentially ion-free, will react with the metal that's in the lab equipment and cause pitting and actually destroy the metal that's in the lab equipment. So if you have a water bath, a CO2 incubator, if you have a glassware washer and autoclave, ultra-pure water is absolutely not recommended for any of those applications. And to be very specific, anytime you have a piece of lab equipment that you would like to feed a type of water, it's always best to look at the operational manual to see exactly what type of water it recommends, because it will normally call out it needs type 2, ASTM type 2 or type 3 water. And then in the second and third arrows, we have the application HPLC again and also cell culture, where ultra-pure water is really an excellent type of water to use in those particular applications because they don't bring along any impurities. So in the HPLC, you're not going to see any organic impurities from the water. You're only seeing peaks from your sample. And true with cell culture as well, you can rest assured that the water that you're using doesn't bring along nucleases and pyrogens and bacteria, that if there are changes in cell morphology, that they're because of the variables you're adding and not because of the water. And we have a question here. Why does any ultra-pure type 1 system, it's limited to not show more than 18.2 megaohm? Is it due to the standard or a limitation in the reading of the resistivity? And that's a really good question. It's an actual, the measurement doesn't exist beyond 18.2. So there's no ability, there's completely, so if you have water and it's completely devoid of ions, there are absolutely no ions at all, the reading would be 18.2. So there's nothing beyond it. There's no such thing as anything beyond it. I hope that helps answer your question. If it doesn't, follow up with another one, and we'll address it in the Q&A. So how does a water system remove impurities? And that's going to bring us to our next survey question.
Thank you, Julie. Do you know the type of purification technology used in your lab water system? Please select your answer using the survey question now. If you have a question for Julie, and some of you do, please continue to use the Q&A module in the lower right. Julie will be taking those questions that she can address during the presentation in real time. Those that she doesn't, we'll save for the Q&A session at the end of today's webinar. Okay, I'm going to broadcast the results and hand the reins back to Julie.
Thanks, Jeff. So about 79% of you know the type of purification technology in your lab system. I think that's phenomenal. I've asked this question many times before, and the answer is never so favorable. So that's really great. Almost 80% of you have a good understanding of what's happening in your water system. That's wonderful. And let's catch the rest of you up here. So there are 8 different technologies, water purification technologies, that are possible to use to purify water. And of the 8 technologies I've listed here, 7 of them, so all of them with the exception of distillation, all the rest of them, we and other water companies, we use these technologies and incorporate them into water purification systems. So distillation is kind of by itself. It's its own thing. You can purchase a still from some water companies. Actually, Thermo Scientific, we still sell stills. It's one of the first products we ever sold through the Barnstead line. So we still sell them, and we still have really great customers who are using them. But the other 7 purification technologies are the ones that we kind of mix and match in a water system to get removal of impurities and to create the purified water. So the reason we're going to even discuss these technologies, and the reason I'm really happy that I'm pretty aware of it, is that I want you to be aware of the technologies in your water system because they're mostly consumables. The technologies exist as consumables, and they need to be changed periodically. And changing your consumables on time, which is according to your manufacturer's suggestions, it really ensures that the water quality stays consistent. So we're going to do a little bit of a deep dive here about each of the technologies so that you can get, again, more informed as to why they're important, why you might change them, and when you don't change them on time, what can the repercussions be. So we'll start with reverse osmosis. Reverse osmosis is mainly used as a pretreatment method before deionization. This technology exists in its own system. You can buy an RO system. People buy them for the house, again, to purify their drinking water. You can buy a system. They're so simple, and you'll see at the end of the presentation how simple these systems are. So they're great. They're inexpensive, easy to maintain. And you can use them to feed a lot of lab equipment. But this technology, RO membranes, they're also used in larger systems like a type 1 water system that uses tap water. So they're used to pretreat. Reverse osmosis itself is best explained by first talking about the process of natural osmosis. So in the example that I have here, I just kind of drew a diagram for you guys to take a look at. A semi-permeable membrane, which is the red, is used to separate 2 solutions. One is a saline or a salt solution, and the other one is pure water. So each solution is open to the atmosphere. And during osmosis, the pure water flows through the membrane to dilute the salt water in an attempt to equalize the salt concentrations. This natural force is called osmotic pressure. When pressure is actually applied to the salt side of the solution, that natural process of osmosis is reversed. And so water from the saline side passes through the membrane, leaving the saline solution more concentrated. And this is called reverse osmosis. And so for our equipment, in terms of how to put this in perspective for a water system, the saline solution would represent tap water. So we're pushing water, the pure water, away from the impure tap water. And this process, in terms of all the other technology, is pretty slow. So anytime you have an RO membrane that's in a system, you always have a tank because the process is fairly slow compared to all the other technologies. So if we think about the physical characteristics of an RO membrane, it really includes layers of membranes and separating fibers that are rolled really tightly around a perforated center core. And the feed water comes in the end of the housing and is forced through the sides, causing the water to enter the membrane. So any water, the water that gets through the membrane is the good water, and any of the water that doesn't get through the membranes is termed reject. And RO membranes are able to actually purify water to about 90%. So they're able to remove almost 90%, depending on the RO membrane, 90% of impurities. So they're a really great, it's a great technology to use to purify tap water. And deionization, or ion exchange, is a process that pushes water through spherical porous resin beads. And so on the left, I show you one of our cartridges. This is a cartridge full of resin, and the scientist is using the quick connects to connect it into the water system. And if you had a microscope and could zoom in to what's inside that cartridge, you would have what's on the left, which is the cation. It's a mixture of cation and anion resin. So the cation resin removes positively charged ions, and anion resin removes negatively charged ions. And so note that the resins are named for the type of charge that's attached. The actual charge on the resin bead is the opposite. For example, the cation resin has a negative charge, which attracts positively charged ions. So each resin bead has a number of exchange sites for deionization to occur. So if you take a look at the cation resin, you see a number of H pluses. There's a finite number of those places that can attach and exchange for a sodium, an Na+. It's a finite number. And once that cation resin bead is full of the NAs and there are no more H pluses to exchange with, then the term is that the resin is exhausted. And when the resin is exhausted, it can no longer remove any more ions from water. The way that you would know this, and this is again why we even talk about this technology, is I want to empower you guys to know, how do I know when the ion exchange resin is exhausted? When it's exhausted, it can no longer remove ions. When your water is no longer ion-free, it affects the resistivity. So the reading on your water system will change. It will not be able to get to 18.2, for example, if you have an ultra-pure water system. All right, so following on the footsteps of deionization is electrodeionization. And we shorten this to EDI, or Electrodeionization EDI. And it works really in a very similar way to deionization. It's the same concept that you can see in the drawing. There are some resin beads there. The resin works in the same way it does in the cartridge from the previous slide, with the one big exception is when the resin gets exhausted, there's an electric current that keeps recharging it. So it doesn't, in the previous slide with the cartridge, I told you when it exhausts, you got to change it. You throw it away and put in a new one. With an EDI cell, the great thing about it is the electrical current is always recharging it. And so you don't have to change it as often. So with a cartridge, you're changing it maybe every 6 to 12 months, really depending on how much water you're using and how impure the water is that you're starting with. So 6 to 12 months with a cartridge. You're probably looking at like 3 to 5 years with an EDI cell. The only drawback that I can think of when I think about EDI cells would be the cost of the cell. You have to do some math and see if it makes sense for your particular manufacturer, which is more cost effective. And it can be sometimes more sensitive to hard water. Again, depends on the manufacturer, but some EDI cells are pretty sensitive to hard water. So it just may require that you put a softener in front of your system, or it just may not make sense to have this technology in your water system. And I have a question I want to address that came in. It's, what is the best method to keep the RO tank clean from bacteria? And there are a couple of different answers for that. Whenever I was explaining with the RO membrane, you have an RO tank always, and it's true. You dump water into that RO tank, it can grow bacteria if you're not careful. There's a couple of ways in any tank that you can keep it clean from bacteria. The best way always is to make sure that you have a tank that's the right size for your usage. You want to empty that tank every 1 to 2 days. So getting the right tank from the start is the easiest and best way to prevent bacteria growth. If you don't do that, or you can't do that, or you want some extra incentive to make sure that water stays clean, a lot of water systems will recirculate tank water. So they'll take the water that's in the tank, pull it back into the system, run it through the purification steps, and take it back to the tank. Or some companies offer UV lamps, which is the slide we're on right now. And the UV lamp will actually it can either sit in the tank and keep control of the bacteria, or the UV lamp is in the system. And again, the water gets recirculated through the system and back into the tank, and the UV lamp will control bacteria. So we'll talk about that technology next, UV oxidation. UV oxidation is really the technology that is responsible for bacteria control and the oxidation of organics in water. So typically, again, in a type 1 water system, that UV lamp is going to have 2 wavelengths. It's called a dual wavelength lamp. It's 185 and 254 nanometers. So the first wavelength is responsible for the photochemical oxidation of the organic impurities in the water. So basically the water moves past the UV lamp. In the picture you can see what you see is a stainless steel. That's the outside of the container that the UV lamp is sitting in. And the person in the picture is plugging that lamp into the system. So the water moves around the UV lamp. The water is zapped. Any organics that are in the water are oxidized. The wavelength 254, that's the wavelength responsible for bacteria control. So when you have a tank that has a UV lamp in it, any company, it's only going to be that single UV light wavelength. It won't worry about oxidizing organics. It'll just worry about the bacteria control. So even type 2 systems, RO systems, if they come with a UV lamp, it's going to be that single wavelength. If you purchase a type 1 water system, you'll get both wavelengths. You'll get a dual wavelength UV lamp. So again, the advantage of having a UV lamp in a water system is that it will oxidize the organics. It'll enable the system to remove the organics, and you'll get down to a total organic level of less than 5 parts per billion. So again, just to emphasize, if you have an application and it's sensitive to organics, you could purchase the option of a TOC analyzer, a total organic carbon analyzer. It would give you a real-time readout of where you're at with the level of organics in your water at any time. And it will, you will always choose the option to have it with a UV lamp, right? Because the UV lamp is the technology responsible for oxidizing organics. Adsorption is, if you think back to UV oxidation, it oxidizes the organics. You still have those species in the water. So adsorption is a technology. It usually lives in the ion cartridge. The activated carbon is mixed with the resin in a cartridge. And it's responsible for removing any residual organic impurities and any chlorine that might be in the water. So in organic adsorption, the impurities in the water form a low energy chemical bond with the surface of the activated carbon, and they get removed from the water. And distillation, I talked about that kind of earlier. It's a technology that tends to live by itself. And this is a very crude drawing, but during the process of distillation, pure water is actually removed from the impurities, unlike the other purification methods. So in distillation, water is heated to its boiling point and undergoes the first of 2 phase changes from a liquid to a vapor. The solid ionic materials, particulates, microbes, all of that dissolved organic materials, it stays behind in the heating vessel. and the pure water vapor rises, enters the condenser, and then changes back its phase from vapor to liquid so that you have purified water in the collection vessel there. So there's benefits and challenges with a distillation unit. And the benefits are there are no filters to change, and you can completely shut the system down during the summer. And so we tend to find customers who are most interested in stills. We find them in like secondary ed, high schools, community colleges, that they need to shut the system down for the summer because it's really very easy to do. We also find them a lot in like the emerging markets and areas where they may not be able to have the budget to continue to change filters like they might want to. There's also very high capacity. Stills can produce a lot of water. So if you need a lot of type 2 water, then a still is a good option. So the challenges of a still are they really are high in resource demand. So they require a lot of water to cool down the purified water, and they also require quite a lot of energy and electricity. And ultrafiltration is a filter technology. It removes select components through size differentiation. So particles that are larger than the selected pore size of the ultrafilter are removed, while particles below the size obviously can pass through. And you'll find this filter, most water companies, water purification suppliers, we sell some version, everybody sells a version of an ultrafilter. They're very useful for people who are interested in nuclease-free and pyrogen-free water. You got to have it. But there's two ways that a manufacturer can sell this ultrafilter. Some manufacturers, like Thermoscientific, we incorporate the ultrafilter into the system. So when you purchase the system, it comes already installed. It's in the system, in the path of the water. The reason we choose to do it this way is there's a rinsing mechanism that's always happening alongside the purification. So because it's a filter, the pyrogens, the particulates, things tend to collect on the surface of the filter, and it would spoil pretty quickly unless you rinse it. And so when the ultrafilter is inside the system, it allows for the filter to be rinsed continuously, which extends the life of the filter to an average of 2 years. There are companies who have this and offer this system, this ultrafilter outside of the system. It connects like a point-of-use filter is what we call it. It sits outside of the system. There's no way to rinse it. And because of that, the filter will spoil within usually about 3 months. They tell you to change that filter. So along with a UV lamp, an ultrafilter is your best friend when you're trying to produce nuclease-free and pyrogen-free water. So if you're doing applications in the life science, molecular biology, in that realm, you would want to purchase an ultra-pure water system with a UV lamp with an ultrafilter. And then you'll have nuclease-free and pyrogen-free water on demand. Filtration is the last purification technology, probably the simplest. It's just this green filter. You're probably familiar with 0.2 micron filters. You filter solutions in your lab to remove any kind of bacteria that's there. We have this filter. It sits at the end of the system. It's the last things the water sees before dispensing for you. And it's just an absolute filter. So anything larger than 0.2 microns can't get through the filter. The slide, this is another slide, another picture that we've taken from the water book. I like this picture because it gets one simple message across, that there are a lot of technologies out there. There are a lot of impurities out there that you have to worry about. And unfortunately for us, there's not one purification method that takes care of everything. So a water purification system, particularly one like an ultra-pure water system, because ultra-pure water is free of everything, it really has to employ a lot of these purification technologies to get the desired product. So I told you we would take a peek inside of a water system, and this is my peek into a water system. This is a type 1 ultra-pure water system, and it is being fed tap water. Type 1 systems, you can purchase them. One type will only be fed on pre-treated water. So the water already has to go through some purification steps before it goes into the water system. Or you can purchase a type 1 water system that you can feed directly on tap water. So that's the most complicated system. That's why I'm going to show it to you here. Tap water has a lot of stuff in it, as you can see in the diagram. Once it goes through the RO membrane will take out about 90% of the impurities in the water. So it does a good scrubbing. There's nothing that's gone. It doesn't take anything 100% of the way out, but it does reduce the amount of impurities in the water. And because there's an RO membrane and that technology is flow, we have a tank to capture the water, so that when you are calling on the system to give you the ultra-pure water, it gets pulled from the tank. Because, again, that RO membrane, pretty slow. So in the tank, there are filters to help keep bacteria and ions out, but it tends to not shift in purity too much. The water is then pulled through a UV lamp, which oxidizes the organics. And you can see in the droplet, they're still there. They're just oxidized. So it's really the job of the ultra-pure cartridge to remove those ions and any residual carbon that could be still in the water. And after the ultra-pure cartridge, then all you're worrying about really is nucleases and bacteria. Those will get removed with a combination of the ultrafilter and the filter. So at the point you're dispensing, you have ion-free, bacteria-free, organic-free, nuclease-free water, and in this particular configuration. If we were to look at a type 2 water system, again, type 2 is a little less pure. There are generally fewer options with a type 2 system. So we always start with tap water with a type 2 system, always. It'll go through the RO membrane, sit in the tank. Notice that the lamp here is a single wavelength. It's just there to control bacteria, not to oxidize organics. The water goes through an ion cartridge to remove the ions. There's a little bit of a wording game here. In the previous slide, it was called an ultra-pure water cartridge. Here it's called a pure water cartridge because the resin mix is a little different. So that the water that you're dispensing is not ultra-pure. It's not completely devoid of any impurities. It does still have impurities in it, but much fewer than with where you started. RO water systems, hands down the simplest systems. Tap water goes into RO membrane and dumps into the tank for safekeeping until you need it. So that was a quick overview of the different Pure Water 101 with the impurities and the technologies, and then finally a peek inside the system. A lot of the material that I used in this presentation can be found in our water book, along with a lot of other great helpful resources at thermoscientific.com/purewater, where you'll have access to videos, presentations, and a lot of literature and technical information.
Thank you, Julie. That brings us to our Q&A session. We've received several questions, and please do keep them coming. Before we get to those, though, I'd like to draw everyone's attention to some links now on your screen. The first is an attendee survey found in the right column. Let us know what you thought about today's session and suggest future webinar topics. Also, at the bottom of the screen, we've included a trio of resource documents related to today's discussion. The first is the aforementioned water book, a comprehensive guide to lab water, including a product catalog. Also, a pair of water purification additions to our popular Smart Notes series. Okay, that's enough for me. Let's dive into our questions for Julie. Our first question: what is the max amount of time RO water can be stored in a storage tank? This particular user says the tank has no UV lamp and water system is being switched off at night by a customer.
The max amount of RO, so anytime we think about storing water, it's kind of the same rule applies no matter what type of water, if it's type 2 or RO water. You always want to turn over the water in the tank every day to every 2 days at the very most. That's the best way to keep the water bacteria free. And it's completely based on how much you're using in your lab. There are some features that have come out. Certainly from Thermo Scientific, we have some smart water tanks where you can actually tell the system, even if you had a 100-liter tank, if that's what you purchased from us, if it's a smart tank, you can tell the water system, I need you to only be a 30-liter tank today because we're not going to use much water for the next few weeks. So we're becoming more savvy with how to help customers control bacteria in the tank, but that's the very best way to do it. Secondary to controlling bacteria by your usage really would be the option of a UV lamp that sits in the water tank. That's what some companies offer. Or a lot of water systems, like some of our systems, employ a pump in the tank, and the pump pumps the water from the tank back into the system so that the UV lamp that's already in your water system, it'll keep your tank water nice and clean because it'll zap the water and recirculate it and put it back into your tank. So it depends, again, the best way to control bacteria always is making sure that you're emptying that tank and using the tank every 1 to 2 days.
Our next question. On a tap water system, what is the maximum hardness before a softener needs to be installed?
It really, really depends on the system. It's very specific to the system, and it should be called out in the manufacturer should be able to tell you when you go to order it where that cutoff is. There's always, with water systems, there's always going to be a set of specifications that the feed water must meet to make sure that the water system works properly. And if it's sensitive to hard water, they should call that out in the specifications.
Our next question. What's the most green way to remove impurities?
The most green way to remove impurities. I never really thought about that like that. I can definitely call out there are some not so green ways to remove impurities, and distillation would probably be at the top of the list. It's just pretty heavily, again, it really relies on a lot of water, a lot of cold water, and a lot of electricity to make that system go. RO membranes also have it depends on the manufacturer, it depends on the system what the rejection rate is. It's something that you can ask the manufacturer. It should be listed in the manual what the rejection rate is. So for every 5 liters of water you put into the system, maybe 3 liters is rejected. So you can ask for the % rejection for the RO membrane. It's different for every system. It's different in all our systems, different by manufacturer. EDI still has a rejection stream, so you get waste there. DI cartridges you don't. UV lamps you don't. Get a little bit of waste with an ultrafilter because it's rinsing. So, at the top of the list is distillation. At the bottom of the list probably is DI cartridge.
Thank you, Julie. Our next question. How can I determine what impurities exist in my lab's feed water and what system would best remove whatever junk is in there?
So there's different ways to do it. In the simplest way, if you're thinking about feeding a water system tap water, you can get your county's water record. I mean, you can call them up and figure, they'll send you a report in what's typically in your tap water. Thermo Scientific, we do offer a service, and it's through the link, the thermoscientific.com/purewater. It will lead you to something called an H2O Select Analysis Kit, and it's a free kit where you would sample your tap water, take a sample of it, fill out the questionnaire that comes with it, and send it back to us. And our water experts will analyze your water, and we'll send you a report about the impurities that are going to impact the life of your water system. And they'll give you an idea actually about what water system would work best for you, because you're going to tell them things like, I use 10 liters of water and I do HPLC every day. So when you give them that information, then they can come back to you with an idea of what system works best in that circumstance. And that's really helpful. And it will also help you kind of budget, because it'll tell you also how long your cartridges will last on average. So if you want to, if you're considering a thermoscientific system, I would 100% suggest it. It's a free service. I would do it. If not, if you're thinking about another system, or you just for your own knowledge want to know what's going on, then you can request that information, usually from some sort of government, entity. I'm thinking U.S.-based, but I'm sure anywhere in the globe you can get that kind of information.
Thanks, Julie. If you permit me for a moment, the H2O Select Water Analysis Program is absolutely available through thermoscientific.com/purewater, as Julie mentioned. A direct link for those interested would be thermoscientific.com/select. Okay, our next question. Is it common to go from tap water to type 1?
Yeah, it's actually becoming more and more common. I think of all of the types of water systems that we sell, that segment, that customer segment is kind of booming right now. And I think it's because budgets get cut when universities are being built and pharma companies are being built. One of the things that sometimes I think they see is, we don't really need a central system. And so they cut that out of the budget, and now customers don't have pre-treated water in their lab. So historically, we didn't see that a lot. Now we see it a lot more. And so when you are trying to go from tap water to type 1 water, it's important, definitely, I would say critical, to get a report on your tap water. A type 1 water system isn't inexpensive, and you have to maintain it. Every year there are consumables that have to be changed. And depending on the quality of your feed water and how much you're using, you're going to be changing those more often or less often. So if you can get a heads up about what the impurities are in your tap water, number one, you could buy, we offer all the time, when we see like maybe a customer has a crazy high amount of organics in the water, we can recommend that they put a pretty inexpensive filter right in front of their system, and it saves them a lot of money going forward. So knowledge is power. If you know what your tap water is and what the quality is, then you can better prepare and have a better experience with your water system.
Our next question. How can we know how effective is EDI operation in removing impurities? Does it change over time or degrade over time?
No, it's really like a DI cartridge. It's either going to work or it's not going to work. And the way that you'll be able to monitor that, again, it kind of depends on what manufacturer you have. But normally there's a menu option. You can go into the menu and you can actually see what the conductivity or resistivity of the water is before and after the EDI cell. So you could kind of diagnose a problem there. But you would probably know right away if something was going on with your EDI cell, just based on the resistivity or conductivity, whichever you have reading, you have the system set at. So if the system normally reads 15 megaohm and it can't get there, it's only getting to 5, a lot of times that's the issue. It's back to the EDI cell. So that's not something I would ever try to troubleshoot on my own. That's a good call for the tech support of your manufacturer. They'll help you troubleshoot that.
Now I know that we're coming up on the 1 hour allotment. We still have questions in the queue, so we're going to stick right here and answer those, or as many as we can get to. If you can stick with us, please do. If you do need to jump off and you've asked a question, we will try to address those offline and follow back up with you. Our next question, how long should a lab store double distilled water before using?
I would say We, back in the day when I was a graduate student, we stored water that we probably should never have stored, and it worked. So my first comment would be to you, if it's been working, then continue to do it. It's not going to hurt anything. In general, anytime you store water, and even double distilled is in the type 2 category of water, it's pretty pure. The longer it sits in the container, the more interaction it has with the atmosphere. It's going to pull CO2. The TOC level is going to increase. It's going to pull organics from whatever the side of whatever you're holding it in, whatever the tank is. It's going to pull organics. It could be exposed to bacteria. It's never good to store water, period, ever. But if it's working for you, I wouldn't worry about it. And, if you can avoid it, because you will start to introduce impurities. And I think the worst part just is you'll have an inconsistent water source. Because if you double distill your water and you store it for a week and then you use it, and then the next time you use it fresh, it may impact what you're looking at because it's been stored for a different length of time, and so the impurity level is different. If you're just making buffers and media from double distilled water, probably doesn't matter at all because nothing is that sensitive that it will pick it up. But if you're doing something kind of sensitive with it, then I would try to avoid it. Sorry, that's not an easy answer for that one.
Our next question, which hopefully will have an easy answer. When the ions are getting exhausted, does the water purity fall immediately or slowly? And how can we know if cartridges are getting exhausted by looking at the values?
Yeah, it'll go immediately. So it's not a gradual thing. You won't see, like if you have an ultra-pure water system, you're used to 18.2. If you come in the next day, and it won't be at like 16 and then 15. It'll be like, 1. It really will drop off very quickly. So as soon as it does that steep drop off, it's time to change the cartridge. And I would just say if you're changing it more frequently than not, then start thinking about, has the quality of my feed water changed or am I using more water? Because those two things are big influencers on cartridge life.
We're asked, what are the specifications for tap water?
Ooh, that's, the million-dollar question, right? It really depends on where you are in the country. Folks, I have customers in Germany, and they have, like, amazing tap water that's, like, really, really great purified water that could almost be swapped for pre-treated water. And, I live in the U.S., and the middle of the U.S. has pretty high organics in the water. So, again, rainy season, I have a huge impact on filters during the raining season. We hear about that. So really depends where you are, what time of year it is. It's all over the place. Even your tap water, you should get tested, not just once, because that's like kind of a snapshot of what's going. Every quarter or something would let you know if you're seeing big changes. And I say tap water, but that includes your pre-treated. If you have a central system, it's not a bad idea to have that tested because you're usually relying on a facilities group to maintain that system. You're not doing it. You don't know how often things are getting maintained properly. So it's always good to keep an eye on the feed water. It's been such an issue, actually, that the newest generation of thermoscientific systems, all of our type 1 water systems now come standard with a feed water monitor on them. So it will alert you if the feed water quality has changed drastically so that you can take steps. You can, disconnect or take whatever steps you need to take. It's been such an issue that feed water quality can change and shift, and then you won't know it until your cartridges are running through very quickly.
Our next question, how can we best predict cartridge life?
The best prediction for cartridge life is really following whatever the manufacturer has in their manual. That's the place to start. I would say look there first. And if you're really off the grid, if the manufacturer is saying 6 to 12 months and you're changing every 2 months, that's a really good reason to call their tech support and see if you can troubleshoot what's going on there. But I would start with the manufacturer's suggested cartridge life.
We'll take a couple more. When is it best to use an EDI system?
We tend to quote EDI systems for customers who need a large amount of water, probably because our EDI cell is in one of our water systems that produces a lot of water. So it's the only time really not to use an EDI system would be if you had trouble with your feed water, if the quality was inconsistent, or if you had a lot of hard water, that I wouldn't suggest it. Or you definitely would need a softener in front of it.
Okay, I think we're going to take one more question and then wrap up. If we didn't get to your question, we will try to address those offline. We'll follow back up. And if you have further questions, you can email Julie directly at julie.foster@thermofisher.com. Our last question, in order to remove these contaminants, do I need multiple systems or will one system work for all?
Well, an ultra-pure water system, if you meet the incoming feed water requirements, it should take everything out of your water. When it's configured with a UV lamp and an ultrafilter, it should take everything out. That solution doesn't always work for every customer. That would be like a tap to type 1 solution. Sometimes the right answer is multiple water systems. So a scenario that I could think of is you're a customer who wants to feed a glassware washer, an autoclave, or a CO2 or something. You want to feed a piece of equipment, and you want to have type 1 water. Then you could think of a configuration where you have a type 2 system. You feed the tap water into the type 2 system into a tank. From the tank, you can feed the different pieces of equipment in your lab and feed the type 1 system. And then the type 1 system would produce ultra-pure water for you. So I think, if you need a lot of water, that's always a good configuration because it tends to be more cost-effective than one system. But it kind of a lot of nuance there. And again, the manufacturer is going to have such a good knowledge of their products, it's probably best to give them a call and walk through your scenario and see what they recommend.
Thank you, Julie, and thank you all for attending today's webinar. Again, please feel free to send any further questions directly to Julie at julie.foster@thermofisher.com. You will receive an email within the next few days with a link to the recorded archived webinar. And visit thermoscientific.com/labwatersource for future webinar details and, as this series grows, to access any of our recorded on-demand sessions. Thank you all again, and have a great day.